Good day. I hope your day is going very well for you. Welcome to the exida webinar. Today we're going to be talking about FMEDA, that's Failure Mode Effect and Diagnostic Analysis. And very specifically, we're going to be talking about how to do FMEA faster and better by getting the information we need right up front. I managed a group that did many FMEAs over the years, and when we first started, I was truly frustrated at many projects that went over budget and behind schedule. And when we dug into it, we found the main reason was we just were not getting the information we needed from the designer to finish the FMEDAs. I mean, we could get started, but we couldn't finish without all the information we needed. And given that we don't want to be very frustrated, over budget or behind in schedule, we decided to do something about it. And today I'm going to explain exactly what we've done at exida and realize that we did this so we could do a better, faster job. And we've created a tool called ARCHx, which allows us to gather the information rapidly and in a very organized way. If you're doing FMEAs, please consider adopting the techniques we're talking about because we found them to work. For those of you who don't know exida, I just want to comment that over the last 25 years, we're proud that we've grown into a top, strong global company with a lot of technical experts, primarily in the field of functional safety, alarm management, and cybersecurity. exida, as a large corporation, does project services. At systems level and at the product level, we have tools to help in all these areas, and exida is an accredited certification body and a notified body for the EU. One of the exida companies is called Exida Innovation LLC. This company does engineering tools. Excellentia is a tool for systems level design. Silstat is a collection of tools for operations and maintenance, especially for gathering up event data in the field, demands, failures, and so forth. Finally, OEMX is a suite of tools for integrated development process engineering. That's where we're going to be talking today because the FMEDA is part of the OEMX suite. Some of you may not really understand what an FMEDA is, and we're going to talk about why. Why do you even do it? And there's people who are still arguing today, well, this is a waste of time. We're not going to be doing any FMEDAs. Well, for many reasons, business and technical. It's desirable to understand and predict the failure rates that a given design may experience when deployed. In fact, in most cases, we need the failure rate numbers for each failure mode. And that analysis really needs to account for the automatic diagnostics added to the design and any latent fault test or proof test, it's sometimes called, to generate these essential metrics. The FMEDA process was created to meet these needs. And we do have a white paper explaining that if you'd like to dig in a little deeper. An FMEDA is defined as, let's say, a component level bottom-up analysis using quantitative failure rates for each component and each component failure mode. These are mapped into the device level failure modes, each component contributing a certain amount to each device level mode. Automatic diagnostic detection capability, one of the most advantageous methods for achieving functional safety, Automatic diagnostic capability is used to classify these different failure modes into those that are detected and undetected. And latent fault test coverage is then used to separate the dangerous undetected failures into dangerous undetected by proof test and residual dangerous failures, which is like kind of the worst metric of all, and we don't want to see that happen. We want to minimize that number. Useful life is an important part of the metrics that all of you reliability engineers understand. All of this should come from a good FMEDA. When we first invented FMEDA back in the late 80s, we used a technique called direct mapping. We would look at a schematic diagram, and our very experienced designers who could look at a schematic and pretty quickly understand what was there and why would go through it. We would get component data, including failure modes and failure rates for each failure mode, and we would directly map them into the device level failure rates, one line at a time, often using a spreadsheet. We would have to trace through the circuit, through the later circuits, all the way to the safety output, back and forth, tracing through the design. It was kind of fun, but it was also a bit tedious. Today, we call that the old way. What do I mean by that? In a typical FMEDA project, back some years ago, we would start with the important things of a hardware schematic, a bill of material, and component specifications. And we were thinking, boy, what more do I need? I don't need anything else. Let's get started. And then we get going, and all of a sudden, we hit a certain part like C30, and we know it fails with a high leakage current or perhaps even a short circuit. And if that happens, we know this 5-volt output drops or goes to 0. And we can usually figure out what the device level impact of that is, safe or dangerous or annunciation or no effect. But then we wonder, gee, is there an automatic diagnostic to detect this failure? Or is there a latent fault test? Or is this a failure that doesn't go detected for the life of the instrument? Well, we don't know that. Okay, call the designer. Let's get an answer. I'm going to call him up. He's going to answer and give me the response immediately. The designer says, I'm busy. I'll get back to you. And he gets back to us a week later and said, what capacitor? Where are you? Which schematic? What sheet? Which capacitor? And after a nice short half hour or perhaps even 1 hour discussion, we get an answer. And we have to resume the FMEDA. Now, where were we? C30. Let me find out. Where did I store that file? And you can imagine that one of the key reasons why we had over budgets and schedule delays. So instead of thinking we have everything we need, we really sat down and figured out what do we really want before we start an FMEDA and what documents will provide this information. Well, we need to know what automatic diagnostics are planned for this device. We need to look at the architecture design and the functional blocks and the functional failures of each block. And we need to know, and this is exactly where we should be mapping those functional failures into the potential device level impact, safe, dangerous, annunciation, no effect, and so forth. Number 3, we need to know how good is the diagnostic for this particular failure mode of this particular block. A diagnostic may very well have different diagnostic coverage factors for different blocks and different failure modes. And we need to know what action is taken when a diagnostic detects an internal failure. Lastly, if there is any opportunity for latent fault testing, and normally there's some opportunities, what is this test? And then how effective is that test for any given functional failure mode and any given block and functional failure mode? Given this information, we've come up with an approach which we call the functional failure approach, the second way of doing an FMEDA. And we've already had one webinar on that, and there's a nice white paper on our website describing this in a lot of detail, so I won't. But I can tell you, we do an FMEDA, and we look for the architecture design blocks. That's typically entered in a conventional DFMEA. Perhaps we can get all that information from a DFMEA. And sometimes the automatic diagnostics are documented, but most commonly not sufficient detail, but that's all right. And for all the automatic diagnostic mitigations, we need to know, we have to estimate how good that diagnostic is for each potential block and each failure mode of each block. Then we look to see if there are any potential latent fault tests. We describe them with their test effectiveness coverage, their test coverage, and document all this. Then, the potential impact of each block failure mode is documented at the device level, safe, dangerous, enunciation, and so forth. And given that information, the FMEDA can be done relatively smoothly by entering the components for each block. And each component failure mode is mapped to the correct block failure mode. For example, look at this power regulator block. I see 1, 2, 3, 4. I see 10 components here. So for each component, we go into the tool, the FMEDA tool, and we enter the component type. We ask for a list of well-known, proven failure modes. We ask for the failure rate for each failure mode. Hopefully they get automatically loaded rather than typing them in. And then we map each component failure mode to the functional failure mode of the regulator block. For example, if that integrated circuit fails with no output, we're very comfortable in saying the regulator block output goes to 0 volts. And we classify that according to the mode, safe, dangerous, and it goes into the device level failure modes. And you can see it's really a lot easier to focus on one block and the failure mode of each block one at a time than it is to trace back and forth through many different blocks and many different rounds of components to figure out exactly how these things are properly mapped. Now, we are using the ARCHx tool because we not only wanted to follow this process, but we wanted to follow it with a lot of help because that makes it faster and better. We document the information also, and it generates nice reports, and everything's all clean, and it's really good evidence for certification projects. So based on the architecture design, we enter each functional block with a screen called Load Unit Knowledge. Now the Load Unit Knowledge screen, and we pick it from a unit type category, which is a pull-down list, suggests deviations in light blue and potential mitigations, including automatic diagnostic functions. Now, we know you delete the failure modes that are not relevant to this design by unchecking them. you check the mitigations, including the automatic diagnostics. And I can see I pulled up the data sheet for this particular regulator chip, and I see it does have an under voltage protection monitor built for the input power. And so we're going to check the boxes M9, M10, and M12, and that gives us some mitigation for those particular failure modes. Then I press the load button, and it goes into a tree, which will be showing you the architecture hierarchy of your design. So the first point is we need to know what automatic diagnostics are planned. And there it is. In the pink, we have a low voltage monitor. We have documented planned mitigations, and we got it with a helper checklist, which really helps make things better, but I'm not sure what's more important, better or faster, but boy, it sure is nice when you get both. Keep going. I need to know the architecture design blocks and the functional failure modes of each block. So for any given unit, and that's the beige color here, we need to know what are the failure modes. We've got that. And for each failure mode, we want to know what's the impact. So to document, choose, and document impact, we go down to a pull-down list, which gives us a set of the 61508 failure modes. We pick the one that fits for this particular failure mode of this particular block. Wow, that's fast. I've got a nice list to pick from. I don't have to come up with potential impacts all on my own and type them in. But you do have to stop and think. I mean, I'm not saying this is a check the box kind of a solution. This is just a tool that helps you by giving you checklists and assistance. You still have to decide what failure modes exist, what mitigations are planned, and think it through. This analysis still requires understanding and thought. Item number 3, how good is the diagnostic coverage? Okay, we know we have a diagnostic. We have a low voltage monitor that can detect 0 volts. And quite frankly, for 0 volt low voltage monitor, we're convinced they always work. So we're going to give it a high diagnostic coverage of 100, and that is already suggested by the knowledge base. I didn't have to type anything if that's correct. Whoa, I like that. And again, we have a documented diagnostic coverage for this failure mode for this block with known coverage ratings provided in the knowledge base. Now, if the knowledge base is not correct for your design, you can go in through a pull-down menu and select none, high, medium, or low. And if you really feel you can justify a more precise estimate, you can enter the actual diagnostic coverage percent. I'm not sure I recommend that. It does slow you down, and it usually isn't that significant. 95 versus 99, stuff like that. Maybe someday, but right now it's usually not that significant. And you have to justify it, which is a little hard to do. Whoa, we knocked off the first 3 items. That's great. How about number 4? And I've highlighted that in yellow because what does the design do when this mitigation, this diagnostic, detects that the 5 volt went to 0 volts? In this case, it's a 3.3 regulator. Anyway, what happens? Well, normally we can select that from another pull-down menu, which contains the most common, regularly used action taken. And of course, if it's one of those is valid, you just select it and move on. If you need a special one, you can type it in yourself and it will accept your special action taken. Oh, I love it. Documented action taken on a detected failure using a helper checklist. Faster and better. Now, some of you may not even know what this concept of a latent fault even is. But we define a latent fault as a test that can't be done while operating in the safety protection mode. Now, normally that's because the test itself might cause a false trip or might cause a potentially dangerous condition temporarily. But if we go offline, like during a startup, that's a latent fault test. Other latent fault tests are a calibration check, a sequence of operation, exercising a mechanical device. When you start thinking about it, there are all kinds of things that are potentially possible, and they can all detect failures that aren't detected by the diagnostics. And that's what we are trying to do. For any given latent fault test, we need to estimate what are the chances that this test will detect this failure mode in this block. And there's a place to enter that. We're right on the deviation node editor. We name the latent fault test, estimate the test coverage, and save the results into our documented FMEDA database. Now, normally, that's really not enough. We also have to describe the latent fault test in more detail, and you can click on the latent fault test editor, type in all the extra details and any notes you want about this particular latent fault test. Document and justify. I think we've done a pretty good job. Let's just run through the checklist. Do we understand what automatic diagnostics are planned? Yes. And they're documented. Do we understand the potential impact of each block failure mode? Yes. How good is that diagnostic coverage for that specific block failure mode? We have that documented. What action is taken? We've got that. Is there a latent fault test? If there is, that's now been documented. And we document the latent fault test coverage. That's the information that an FMEDA needs to proceed very smoothly. At that point, you can go into the FMEDA button and start entering the components for each block. And the beauty of this is all the information we entered above goes right into the FMEDA, and the failure modes for this particular block are displayed for you. When I assign a component, I get the component failure modes. I assign it to a block failure mode, and all the calculations can be done. We think it's important that the ARCHx tool, which is, if you saw what we were doing, you realize that basically we just did a design FMEA, or a streamlined version of a design FMEA, which we call DDMA, Design, Deviation, and Mitigation Analysis. If you already have a DFMEA, of course, you can keep that in your documented information, and this should match up. But isn't it better if the tool that does one task feeds straight into the tool that does another task? And in this case, we use ARCHx to gather the information and FMEDAX to perform the analysis and calculate the metrics. This is working out pretty well. It achieves the OEMX goals of fewer problems, lower total cost, faster time to market, and higher design quality. In our experience, we know that getting FMEDA information can be very time consuming, and especially when it's done during the middle of an FMEDA. Any task is prolonged when one must start and stop. I saw an efficiency expert once called that the loss of context time. Go read a book about that if you wish. The functional FMEDA approach can be very valuable, except a lot of people are a bit resistant because it appears like there's more work up front. And that's just the natural tendency of engineers who just want to get started. Not realizing this helps you get finished, which is as important as getting, or more important than getting started. And the extra time needed up front can be very minimized with a smart FMEDA tool. And when a smart tool feeds the information directly to the FMEDA work goes very, very smoothly. We're pretty happy with what we have created for our usage, and we do offer it to anyone else. Anyone who's real interested in digging in more, you can play and learn. A demo version of the whole OEMX package is readily available. You can send an email to oemx@exida.com and ask for a free 30-day demo. And now note, the demo version is stripped down and it doesn't include the full knowledge base or the full component reliability database. But I promise the real OEMX, if you find you really like it, is a whole lot better than the demo. Now, I'd like to ask if anybody has any questions about what we've covered today and beyond, if it's related, and I'll be happy to answer them right now. If you can type them in, and we'll get our moderator to read back 2 or 3 questions possibly. We have time for that.
So our first question is in, Bill. Is this tool using IEC 61508 or ISO 26262 DC effectiveness?
Oh, good question. We have found that many of our FMEDAs have to be qualified for both 61508 and ISO 26262. But we don't want to do 2 FMEDAs. So we've taken the approach that we will use the 61508 concepts for the analysis because those failure modes are orthogonal and complete, whereas 26262s are not. And then the FMEDAX tool automatically translates from 61508 into the ISO 26262 metrics. So the bottom line is it's not one or the other, you get both. But we're using the superior analysis definitions from 61508. Good question, thank you.
We have another question that came through. Is tool qualification done for this FMEDA tool as ISO recommends using qualified tools?
Another good one, thank you very much. Tool qualification is primarily the responsibility of the end user. But in order to help that and speed it along, Exida does have a tool qualification report where we explain to you how to use the OEMX tools. We refer back to the user manual to look for all the automatic checking mechanisms. In other words, the OEMX tools has a lot of checking to try hard to see if you've made a mistake. Errors of omission, double counting, things of that nature. And the user manual explains all these different error flags that appear on the screen. If you pay attention to those error flags, we classify this as a TI2 and resulting in a tool claim limit of 1. And yet, exida does recommend that even though 26262 does not require any justification for a TCL1, we think it's very important that anyone using the tool completely understands how it works and has lots of experience with that tool. So if you want some experience and you'd like to get a free demo, be sure and let us know. We have time for one more. Any other questions?
No, Bill, there are no other questions that have come through at this time.
All right, then. I thank everyone for attending. I hope you found this to be of some value. If you have any questions that pop up later, do not hesitate to send an email and ask. Thank you very much for your time. Goodbye.